Day 15 of 75, and this one separates developers who pass Java interviews from those who get silently wrong answers. Watch this. I make a tiny class, a transaction with an ID and amount. I create two objects with identical values, drop them both into a hash set, and call size. You'd expect one. Java says two. The set kept both copies of what is logically the same object. No error, no warning, just quietly wrong dedup. By the end of 5 minutes, you'll know exactly why, and the one rule that fixes it. Here's the model you have to picture. A hash set doesn't scan every element when you call contains. It calls hashcode on your object to compute a bucket. Think of it as a numbered bin and jump straight to that bin. That's why lookup is O1 amortized. But our transaction never overrode hashcode, so it inherited object's version, which is based on memory address. Two separate instances get two different hashes, land in two different bins, and the set never even compares them. It has no idea they're duplicates. So the fix is the equals and hashcode contract. The rule: if two objects are equal, they must return the same hashcode. Override equals to compare your business fields, ID, amount, currency, and generate hashcode from those same fields with objects.hash, ID, amount, currency. One line. Now both transactions hash to the same bucket. Equals confirms they're identical, and the set rejects the duplicate. Size returns 1. Verify it before you trust it. Assert a.equals b and assert a.hashcode equals b.hashcode. If those hold, your type is safe in any set or map. Now the part interviewers love. When does O1 break? The hash routes objects to buckets. But if every key returns the same hashcode, every object piles into one bucket. Lookup degrades to scanning a list. ON. A broken or lazy hashcode that returns a constant does exactly this. Modern Java softens the worst case by turning a long bucket chain into a balanced tree, giving O log n instead of O n. But that's a safety net, not a license to write a bad hashcode. Good hash distribution is still your job. Let me show why this matters in real code. Classic two-sum. For each number, you want its complement. The naive version nests two loops scanning for the match. O in superscript 2. Swap the inner scan for a hash set. As you walk the array, you ask set.contains target minus current. That's 101. Lookup instead of a full pass. The whole algorithm drops to ON. Same set, same contract. The speed only holds because contains is constant time, which only holds because hashcode is correct. Everything traces back to that contract. But HashSet isn't always the right set. 3 choices, 3 jobs. HashSet. Unordered. Fastest lookup. Use it when ordered doesn't matter and speed wins. Linked HashSet. Same O1. Lookup, but it remembers insertion order. So use it when you need reproducible output, like deterministic test results or stable logs. Tree set. Keeps elements sorted. Contains is O log n. Slower, but it can answer floor and ceiling range queries that HashSet simply cannot. Don't reach for tree set for plain dedup. You'd pay log n for sorting you never use. Pick by the question you need answered. One more performance trap. A new hash set starts with capacity 16 and load factor 0.75, so it rehashes, rebuilds every bucket once you hit element 13. In a hot path, that's wasted allocation and GC pressure. If you know you're loading a batch, size it up front. New hash set. Expected size times 2, 0.75f. 460 entries. That's 1 allocation, 0 rehashes. And if multiple threads share that set, drop hash set entirely. It's not thread safe. And use concurrent hashmap.new-key-set for safe concurrent lookups. Day 15 done. The takeaway. HashSet gives you O1 lookup, but only if you hold up your end. Override equals and hashcode together on the same fields and verify they agree. That single contract is the real interview question hiding inside every set and map problem in Java. Get it right, and your dedup, your two-sum, your cache is all just work. Subscribe for day 16.